Dear colleagues, my name is Maxim Korenievsky. I would like to present you the system for the CHiME 6 challenge developed by the team from STC Innovations and ITMO University, St. Petersburg, Russia. My presentation consists of several parts. I'll tell you about our efforts on challenge tasks, describe the developed systems, and outline the obtained results. Then I'll make some conclusions and present our final submission. The challenge conditions and tasks are described in details in the organizer's presentation, so I will skip this and move forward. The challenge was divided into two tracks, and we developed systems for both of them. The first track replicated multi-array track of CHiME 5 challenge and aimed at speech recognition on manually segmented utterances. The baseline Kaldi recipe is mostly standard, but includes several important stages. One of them is the training data augmentation, which includes room simulation as well as speed and volume perturbation. The another one is using test data enhancement with WPE dereverberation and guided source separation followed by the MVDR beamforming. The baseline recipe provides word error rate of about 51% and serves as a good starting point for ASR improvement. This is only 5% worse than the CHiME 5 top system. The STC system also used the combination of WPE, GSS and MVDR for speech enhancement, since it dramatically reduces speech recognition errors. However, our goal was to obtain even more improvement from it. Last year, Hitachi and Paderborn University joint investigation on CHiME 5 data showed that the use of the refined utterance boundaries obtained after the first pass decoding can provide an additional word error rate improvement. By default, per-frame speaker activities induced from hard label information are multiplied by the spectral masks after each iteration of GSS. The first modification is using soft activity labels to improve the masks estimates. Soft activities can be extracted from the first pass decoding lattices. However, we found that better results can be obtained using speaker activity probabilities, estimated by a special target speaker voice activity detection model, which I'll describe in more details later. Besides, we added a diagonal regularization of spatial covariance matrices into the beamforming procedure. And finally, we didn't use in the beamforming the 1/3 of connect channels with the least values of the envelope variance metric, which reflects the microphone-to-speaker proximity. Another substantial improvement was obtained when we replaced the original Kinect training data with the data processed by the same front-end, including WPE, GSS, and MVDR beamforming. The presented table showed the stage-by-stage improvements of the results obtained with the baseline system architecture. We also made some important changes in the backend. This slide showed the scheme of our system for track 1. From this scheme one can see that we trained our acoustic models on either mel frequency or gamma tone filter bank lock energies. Input features were distorted with Kaldi spec augment layer, and their statistics computed with Kaldi stats layer were added to the input stream to ensure better stability with respect to data distribution. We also replaced 9 lower layers of the baseline TDNNF model with convolutional layers and deployed recently proposed multi-stride and multi-stream self-attention mechanisms in the rest TDNNF layers. Our models were trained on a dataset consisting of warm microphones recordings and data obtained using 4 versions of GSS with various settings, namely set of microphones used, context length, and number of iterations. We also used the room simulation, speed and volume perturbation included in the baseline recipe. All the models were trained according to the LFMMI criterion and fine-tuned for one more epoch of SMBR training. Finally, we performed lattice fusion followed by MBR decoding to combine recognition results from different models and different versions of GSS applied to test data. Within ranking B, all lattices were first rescored by an advanced LSTM-based language model and then fused. This table presents the word error rate reduction from several backend improvements mentioned earlier. As one can see, the combination of all these techniques reduced word error rate by 6.2% absolute. As a part of ranking B, the regularized LSTM-LM on byte pair encoding text decomposition was applied for lattices rescoring prior to fusion. The LSTM-LM consisted of 3 layers with 248 units per layer. The network was a modification of AWD LSTM with all regularization techniques except averages stochastic gradient descent. The models trained on 1, 3, 5, and 8000 BPE tokens were used in an ensemble, and the model trained on 3000 BPE tokens was the best single model. The described methods allow it to reduce baseline word error rate by about 15% absolute for the development set and by 12.7% for the evaluation set with our best single model. The lattice fusion provided an additional word error rate improvement of about 3%, and the combination of lattice rescoring and fusion in ranking B allowed it to finally reduce word error rate to 30.96 and 33.91% for the development and evaluation set respectively. Let's make some conclusions on track 1. ASR in real-life conditions is still challenging. Data augmentation can alleviate the task difficulty, but the overlapping speech separation looks the most important. Guided source separation is an excellent approach for this, but it can be further improved with using soft activities. And finally, the acoustic model architecture is also important for the overall improvement. Now let's move to track 2. It was more difficult and interesting than track 1, so we paid much more attention to its tasks. Since track conditions prohibit using manual segmentation, the key task of track 2 was obtaining a reliable diarization for the successive ASR. The baseline diarization recipe used the agglomerative hierarchical clustering of X vectors on speech activity detection segments. However, this approach doesn't take into account the overlapping of the speakers. Since the baseline diarization is not accurate enough, GSS cannot be applied directly. That results in a very high word error rate. Therefore, our main intention was to achieve a substantial diarization improvement, which would be sufficient for applying GSS effectively on top of it. We started from attempts to improve the baseline diarization pipeline. Firstly, we used the improved 34-layer wide ResNet X-vector structure trained on the voxcelib data. Then, we replaced PLDA scores with cosine similarities and applied spectral clustering with automatic selection of the binarization threshold instead of agglomerative hierarchical clustering. As one can see from the table, the combination of these approaches provided substantial improvement of DER for both development and evaluation sets and brought even more reduction of Jakar error rate. We tried to determine the primary source of diarization difficulties and found that the main problem is a large amount of overlapping speech. To quantify it, we changed the reference segmentation by leaving only a single speaker on each segment of overlapping speech. And we found that diarization error rate of such segmentation was as large as 25%, and all these errors were due to the miss of overlapping speakers. So, even with the perfect speech activity detection, the clustering-based diarization approaches are in principle unable to reduce diarization error rate below 25% in this task. So, to overcome this limitation, it is necessary to detect each speaker separately. One of such approaches is the recently proposed end-to-end neural diarization. For track 2, we introduced a novel approach inspired by EEND, as well as target speaker ASR and personal VAD approaches. We called it Target Speaker Voice Activity Detection, or TSVAD. Target speaker VAD directly predicts the presence and absence probabilities of each speaker in the current frame. TSVAD takes standard MFCC acoustic features along with an A vector of each speaker as its inputs. It is important to note that TSVAD requires a sufficiently accurate initial diarization to estimate I vectors for each speaker. We used both CHiME 6 data and 800 hours subset of VoxCeleb data for training the TSVAD model for track 2. We also used the probabilities obtained from the TSVAD model trained on CHiME 6 data only in track 1 as soft activity to improve GSS performance. CalDi ASR toolkit was used for the training. Let's consider a scheme of the single-channel target speaker VAD. Input MFCC features are transformed by a 4-layer CNN and then fed to 4 parallel speaker detection blocks. Each speaker detection block is a 2-layer bidirectional LSTM with projections taking an I vector corresponding to speaker as an additional input. It is important to note that the parameters of 4 speaker detection blocks are shared. Then combined outputs of 4 speaker detection blocks are passed to one more BLSTM layer, followed by 4 parallel fully connected layers and 2 class softmax layers on top of them. 4 pairs of outputs produced by the TSVAD model represent the probabilities of the presence and absence of each speaker on the current frame. The training loss is the sum of 4 cross-entropy losses computed from speaker alignment. The single-channel version of TSVAD processes each channel separately, but we suggested that the multi-channel processing may be beneficial. Indeed, we found that the multi-channel WBE dereverberation improves the results of TSVAD and that the averaging of per-channel probabilities provides DER reduction. Inspired by this, we designed a multi-channel TSVAD model, which takes features from several Kinect channels and combines them via a simple attention mechanism. Here, the scheme of the multi-channel TSVAD model is presented. The input channels are chosen randomly for training, and the first and fourth channels are taken at test time. The input features are the outputs of single-channel model speaker detection blocks. All the speaker detection vectors for each speaker are passed through a convolutional layer and then combined by means of a simple attention layer. The combined outputs of attention for all speakers are passed through a single BLSTM layer and converted into a set of per-frame probabilities of each speaker's presence and absence. This slide shows a full pipeline of our diarization system. After the preliminary clustering-based diarization described earlier, the I vectors of each speaker are estimated. The improvements in the baseline diarization turned out to be sufficient to provide a good start for target speaker voice activity detector. The single-channel version of TSVAD is applied to each Kinect channel separately, and then the probabilities are averaged over the channels. These raw probabilities can be used as soft weights for re-estimation of I vectors applied on the second TSVAD iteration. We found that the second iteration provided a significant gain. However, the third one didn't lead to any improvement. Final segmentation is obtained by combining probabilities from several TSVAD models followed by a simple post-processing. This slide describes a simple post-processing of probability streams obtained from the TSVAD model. It includes 11-tap median filtering, simple thresholding, combining speech segments separated by short pauses, deleting 2 short speech segments. An alternative approach consists of using a multi-speaker Viterbi decoder tuned for the best DER on the development set. The diarization results of the successive application of the described approaches are presented in the table. White-ResNet X vectors improved DER by up to 10% absolute compared to the baseline extractor. The use of spectral clustering reduced DER by another 4 to 6%. The first iteration of TSVAD further reduced DER by 8 to 15%. The second iteration added 3 to 5% more. An additional reduction in diarization error rate is achieved through the use of multi-channel target speaker VID and fusion of different models. It is interesting to note that the best ASR results were obtained on the segmentation not optimal with respect to DER, but better in terms of Jacquard error rate. This table showed the breakout of the total DER into three types of errors, namely speaker miss, false alarm, and speaker error, obtained on the best clustering-based system and TSVAD. The last column showed the word error rates obtained with the baseline acoustic model after applying GSS-based front-end. Our best clustering-based segmentation is not good enough for GSS. On the other hand, TSVAD segmentation allows us to perform GSS effectively. Besides, the segmentation which provides the best speech recognition accuracy has a larger false alarm rate, but significantly less speaker error and speaker miss rates. So the false alarms are not very harmful to GSS, unlike speaker errors and misses. Note that the sum of speaker error and miss rates is significantly less than the lowest possible error of clustering-based diarization, which is 25% as mentioned earlier. As I have already mentioned, the strong diarization results obtained with TSVAD made it possible to apply for track 2 the same front-end technologies that we used successfully in track 1, namely WPE, GSS, and MVDR. This process is depicted in the scheme. TSVAD determines the boundaries of segments and initializes soft GSS. Then the same backend as in track 1 is applied. Like in track 1, this leads to a substantial improvement of word error rate. Moreover, the ASR performance gap between TSVAD and manual segmentation is rather small. The recognition results of the best word error rate TSVAD segments are presented in the table. Now let me make some conclusions on track 2. First of all, the task of track 2 was really extremely difficult, but extremely interesting as well. And we are grateful to the challenge organizers for providing an opportunity to work on it. The proposed target speaker voice activity detection approach directly solved the diarization problem with an accuracy which is good enough for performing GSS. To improve diarization, one can iteratively re-estimate our vectors used by TSVAD. To obtain the best ASR results, one should use diarization with larger false alarm rate and less miss errors, instead of one with the best DER. We provided a more detailed description of the TSVAD approach in the paper for the upcoming Interspeech conference. The final slide showed the submission results for track 1 and track 2. One can compare word error rates for both tracks and ensure that the final difference is moderate, despite the dramatic difference in the baselines. Well, that's all. Thank you for your attention.